This is the Introduction to Quantum Mechanics Part 2. So in Part 1 we described how an electron could be better described as a wave function rather than a point-like particle, as a bullet, as it were. And so let's discuss some of the finer subtleties of this experiment, and we're going to introduce a new result of the quantum theory, something else that was measured when we look, right? So first, in the previous part, we did an experiment where we did not look. We pushed a button, ran the experiment, and we just looked at the photographic film after the experiment was run to see where the electrons arrived, and they arrived in this funky looking pattern. There was a bunch of exposure in the middle, and then less and less exposure. We moved out with regions where there was no exposure at all in between them, right? In between where the electrons actually arrived. So when the electron left the electron gun, it wasn't simply a bullet-type particle, but rather a wave of potential that approached the barrier. And when that wave of potential approached the barrier, we've called it psi naught, it diffracted through, and some of it diffracted through slit A, and some of it diffracted through slit B, right? But some of it, in fact, was reflected. So of course we could easily imagine how there's at least a decent portion of the wave that was just reflected away, right? And that's why I've called this a reflective barrier. The reason I've called it a reflective barrier is because it does not absorb any electrons, right? Okay, so this is an idealized impossibility, but for the purposes of our thought experiment, it will help to demonstrate certain ideas. So then psi naught will give rise to, I'll use an arrow to describe that, will give rise to psi A, the amount of the wave that was diffracted through slit A, plus psi B, which represents the amount of the wave that was diffracted through slit B, plus psi C, the amount that was reflected back and didn't make it through the barrier at all. And of course, some right here would be reflected straight back, right? Okay, and so psi C represents all of these possibilities of it being reflected back, right? In fact, you could let this guy equal to the sum of, an infinite number of wave functions, because we see how there would be a bunch of little bitty sources that would arise from, if the electron had a certain probability of being right here, then it would, the resulting wave would have a certain probability of being reflected back like that, and if it had a probability of being right here, then it would have a certain probability of being reflected back like this. And so psi C is just a culmination of all those results. And we ended up with this bizarre interference pattern, and so we noted that psi A and psi B, which are both associated with the same electron, right? They interfere with one another, right? And to say one another, it is sort of implying that there's more than one electron. No, it's one electron, one wave function associated with one electron, but those two sources interfere with one another to give a probability distribution like this, the probability of where the electrons would arrive. And for the physics students out there, you would calculate psi A, you would add the wave functions first, right? And you would get some result here. And then you would take the absolute square of it, which has also been called the complex conjugate, to find the actual probability distribution on the back wall. But for the purposes of intuitive understanding, we just see that the two sources interfere, and we end up with an interference pattern back here, as we described in Part 1. So let's do a new experiment. In this experiment, we're going to put a light right here, and that little light, every time an electron goes through slit A, and we see a flash of light in the region of slit A, we'll mark down, okay, an electron went through there, right? And then every time an electron goes through slit B and we see a flash of light there, we'll mark down that an electron went through that slit. And we're going to set up our electron gun, our electron emitting apparatus, so that it emits electrons that are at regular intervals, right? So that it, once per second it's sending one electron through, right? So if a second goes by and there's no flash in front of part A, in front of slit A or slit B, then we would mark that down in column C, right? For the electrons that didn't make it through. And so we run the experiment and we just start tallying up, right, the electrons. So it might go something like we'll get one, and let me erase these and see. Let's start from the beginning here. We'll get one through A. And then in the next second, there won't be any electron at all, so we'll put a tally there. And then we'll see a lightning flash at B. And then we'll see another lightning flash at B again. So it's totally random, right? And then none at all. And then the next second, we'll see one go through A, and so on, right? And we might end up with something like this, right? With perhaps B having, one more electron than the others, just due to the random possibility of it being the favored result, right? And whenever we go to the photographic film and we take a look at the exposure of the photographic film, which tells us where the electrons arrived at the backstop, we see that there's a group of exposure right here, and that the film has been exposed in line with this slit B right here. So they're in line with slit A, and then again with slit B. And so this is strange, right? This is bizarre, because now the electrons aren't behaving like waves anymore. They're behaving like bullets again, right? So how can we describe this? So the contention was, by Schrodinger and others, Max Born, Dirac, that a wave function behaves in a very peculiar fashion. This is the second addition to the bizarre nature of quantum mechanics. So if you have a wave function like this that describes the information, the position of the particle, right? So taking the absolute square of this wave function will give you the probability of where it could be, right? So this wave of potential, this wave of possibility is described as this. But whenever this lightning flash went off, it collapsed the wave function to one place. And so there was no longer, whenever the lightning flash went off at slit A, the entire wave function ceased to be everywhere on the back side, reflected back. On this side, part B, it simply existed as a very localized region of part A, right? Near slit A. And so as this new localized wave function progressed towards the photographic film, over time it spread out a little bit, but very little, and it didn't have any other wave function to interfere with it, and so it arrived with a probability distribution back here that looks like this. And in fact, if we ran the experiment with water waves, which we ran in part 1, right? Quantum mechanics, the introduction to quantum mechanics part 1, and we had the two double slits, you remember? And we had the back wall with the little scales, at every place, measuring the weight of the water arriving in at the back, right? And we put a little cork, and we bobbed the cork up and down, and it sent water waves out towards the slits. Well, if we cover up one of these slits, if we block one of them off, then a resulting wave will be emitted through only this slit, right? And of course, there'll be parts of it that will be reflected back in all these other regions. But the part of the wave that made it through slit A doesn't have this other wave source to interfere with it. And so if we plot the amount of water arriving at different locations, which is indicated by the scale readings, remember we have a bunch of tiny little scales. I'd encourage you to go and look at part 1 if you haven't seen it. then we would see a large amount of water arriving here, and then less and less water on the way out, like this, right? So the scale readings would read something like this, and this would be a measure of the amount of water molecules arriving along the backdrop, right? And so that looks very similar to the pattern we get if we look at the electron, right? Then the electron, what has happened is we've collapsed the wave function, and now we only have one source being emitted with nothing else to interfere with it. And then the probability distribution of that source arrives at the backstop, and we get a nice bell-shaped curve of where the electron could arrive. Okay? So this is Quantum Mechanics, Introduction to Quantum Mechanics Part 2, elaborating on the bizarre nature of the theory. Okay, I'm going to step aside and give you a clear screenshot. Part 3 is coming.